Only the solvent particles have moved from the solution which is having less concentration to the solution which is having higher concentration. Y becomes CRT, which is the equation to find out the osmotic pressure, right? So C is the concentration, R is universal gas constant, and T is the temperature. Two solutions having the same osmotic pressure at a given temperature are called as isotonic solutions. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 6 of the chapter Solutions. So in last session we discussed about colligative properties, right? And we studied about the 3 colligative properties in last session. They were relative lowering of vapor pressure, elevation in boiling point, and depression in freezing point, right? So when a non-volatile solute is added to a solvent, that is when a solution is formed, what happens to the freezing point, the boiling point, and the vapor pressure we discussed in last session. Right. So, in today's session, we are going to discuss about osmosis and osmotic pressure. So, osmotic pressure is the next colligative property that we will be studying. Before that, we need to be knowing what is osmosis, right? And then we will be studying about reverse osmosis, and the last topic is abnormal molar mass, right? So, as I said, the next colligative property that you will be studying after relative lowering of vapor pressure, depression in freezing point, and elevation in boiling point is osmotic pressure. So, before understanding what is osmotic pressure and going into that colligative property, you need to understand what is osmosis. So, you might be already familiar with osmosis. So, let's see what is osmosis. It is a spontaneous movement of solvent molecules from the solution of lower concentration to the solution of higher concentration through a semi-permeable membrane. Okay, so it is the movement of the solvent molecules or solvent particles from the area of lower concentration or from the solution having lower concentration to the solution having higher concentration through a semi-permeable membrane. So, this is important. Osmosis happens only through a semi-permeable membrane. So, this semi-permeable membrane, it is important because this, as the name suggests, semi-permeable membrane, it only permits the flow of solvent particles. So, let's take this diagram and understand it. So, in the first diagram, as you can see here, yes, the solution is present on either side and you have a semi-permeable membrane, right? You can see here, a semi-permeable membrane is here. So, what happens? The red balls that you can see here, those are the solute. Right. So, in this part or this part will be the concentration of the solution more. It will be here, right? More number of solute particles or more amount of solute means more concentration or higher concentration. So, what is osmosis? The movement of solvent molecules from lower concentration of solution to higher concentration of solution. So, here as the number of solute particles are less, this is having lower concentration, right? So, what happens? The solvent molecules will, it will pass through the semi-permeable membrane from the lower concentration to higher concentration, right? So, the water which is present here, the blue color you can see, that is the solvent, right? So, what happens now? Only the solvent particles will move through the semi-permeable membrane to the next side. So, what happens? See, it was initially here. Now, you can see the concentration has decreased or the level has decreased. So, what has happened here? Only the solvent particles have moved from the solution which is having less concentration to the solution which is having higher concentration. Right? So, I hope it is clear. That is why the level has come here because, the water is the solvent here. So, solvent has moved to the solution part. Clear? So, once more, what is osmosis? Is the movement of only solvent particles from the lower concentration solution to higher concentration solution through a semi-permeable membrane. Even that is important, right? So the membrane which permits the passage of only solvent molecules but not that of solute through it is called semi-permeable membrane. As I said, it only allows the passage of solvent particles and not solute particles, right? So cellophane, parchment paper, pig's bladder, all of these are examples of semi-permeable membrane. I hope osmosis is clear for you. Now let's move to osmosis in some natural processes where you have seen osmosis in your day-to-day life, right? Some natural applications or natural process in which this happens. Yes, the raw mango placed in concentrated salt solution loses water via osmosis and shrivels into pickle. Right, so the raw mango which you put inside for pickling means you put it inside salt solution, right? Yes, water and salt, that is salt solution, you put it inside that. So what happens after a while? The mango shrinks. Yes, it shrivels. Yes, and you get your pickle, right? So what is happening here? Osmosis is taking place. That is, from the mango, the raw mango, the water is going out into the salt solution. Yes, in the salt solution, what is there? The salt is present more, that is higher concentration. Right. So from inside the mango, the solvent, that is the water, is going into the salt solution. So what happens? Yes, the mango shrinks. Clear? Now, wilted flowers revive when placed in fresh water due to osmosis. Yes, we have seen in flower vase, we take water and we put the flowers inside the flower vase. It is containing water. Why we do this? Again, the application is osmosis there. What happens? The solvent particles move from lower concentration to higher concentration. Where will be the lower concentration? It will be in the water, right? So the solvent particles will move from the water to the stems of the plant, right? That way, yes, you can keep the water fresh. That is why we put it inside water, right? Yes. The next one is, people taking a lot of salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis, and this resulting puffiness or swelling is called edema. Okay, so when we intake a lot of salt or salty food, yes, a swelling or puffiness can happen, which is called as edema. That is also due to osmosis. So these are the few natural processes in which you can see osmosis. It's not just three, there are other many applications as well, right? So I hope osmosis is clear. Now moving on to osmotic pressure, which is the next colligative property. So osmosis is clear. Now let's understand what is osmotic pressure, right? So the flow of solvent molecules from the solution of lower concentration into the solution of higher concentration of solute through a semi-permeable membrane can be stopped by applying a sufficient pressure on the solution of higher concentration, and this pressure is called as osmotic pressure. So let's understand. We know that yes, there is a solution and there is a solvent here. Okay, so according to osmosis, what happens? From the solution which is having less concentration to the solution having more concentration, yes, the solvent particles move, right? So that is what is osmosis. So we know that in the solution, the concentration will be more, and in the solvent, only solvent is there, no solute is there, so the concentration is low there. So what happens according to osmosis? Through the semi-permeable membrane, our solvent particles will move from the solvent, that is a pure solvent, to the solution. So this is what is happening in osmosis. Now about osmotic pressure. Yes, that is the pressure that we apply on the solution side. Okay, this pi that is shown here, that is the osmotic pressure. So apart from the atmospheric pressure, we are applying an external pressure which is called as the osmotic pressure. So if we apply this osmotic pressure on the solution side, what happens? Now if we are applying a pressure here, yes, the solvent particles are moving from the solvent to solution side. So when we are applying the pressure, we are stopping the flow of solvent particles from the solvent to the solution side. We are stopping the flow of it. So we keep on increasing the pressure. Yes, we keep on increasing the pressure in the solution side. At a point, what happens? The flow of the solvent particles from the solvent to solution will be stopped. So that pressure is called as osmotic pressure. So that pressure which is needed to be applied to stop the flow of solvent particles from the solvent to the solution side is called as osmotic pressure. Right? So, yes, in osmosis what happens? From lower concentration to higher concentration, the solvent particles will move. Yes, so we are applying a pressure here so that the flow is stopped. So that pressure is called as osmotic pressure. Clear? Now, the osmotic pressure of a solution is defined as the pressure to be applied on the solution of higher concentration just to stop the osmosis. Okay, so that how much pressure we have to apply so that the flow of the solvent is just stopped, that is called as osmotic pressure. Okay, so where we have to apply this pressure, it will be in the solution, right, not in the solvent, because it is having higher concentration. Clear? Right? Now, osmotic pressure is a colligative property because it depends upon the number of moles of solute in the solution and not on the nature of the solute. So, if more number of solute is present, that is, if more concentration of the solution is there, then more osmotic pressure have to be applied. Yes, more pressure have to be applied to stop the flow, right? So, even osmotic pressure is a colligative property because it depends on the number of moles of the solute which is present and not on the, yes, nature of the solute. I hope it is clear. So, now moving on to the equation by which you can calculate the osmotic pressure, right? So, for dilute solution, it has been found experimentally that, yes, the osmotic pressure is proportional to the molarity. Right? It is molarity. In the case of depression in freezing point and elevation in boiling point, we understood that, or we studied that, yes, the elevation or the depression is directly proportional to the molality. Right? So, in the case of osmotic pressure, it was experimentally found that osmotic pressure is directly proportional to the, yes, molarity. That is the concentration of the solution at a given temperature. That is, it is directly proportional to the molarity. Okay, yes, so pi is directly proportional to the C. So, the pi is the symbol which is used to represent osmotic pressure. Yes, so to remove the proportionality, what do? We add a constant. So, pi will be equal to CRT. Yes, pi becomes CRT, which is the equation to find out the osmotic pressure, right? So, C is the concentration, R is universal gas constant and T is the temperature, right? So, R is the universal gas constant and T is your temperature in Kelvin scale. Yes, so pi is equal to CRT. Clear? Right. Now, coming on to how you can calculate the molar mass of the solute using osmotic pressure. So, we studied how we can calculate molar mass from elevation in boiling point, depression in freezing point as well, right? So, we will see here. So, we know that pi is equal to CRT is the equation. So, what is C here? C is the molarity. So, how do you calculate molarity? Molarity is number of moles present in 1 liter of the solution, right? So, how you can write C then? C will be equal to number of moles of the solute. Yes, A stands for the solvent, B is the solute, right? So, number of moles of solute by volume. Yes, volume in liters. So, how the first equation can be written now? Instead of C, you can write NB by V. So, the equation becomes pi is equal to NB by V. What is left there? RT, right? NB by V RT. Now, NB, what is NB? It is number of moles of solute. How do you calculate number of moles of solute? Yes, it is the mass by molar mass, right? How you can write this? Mass by molar mass. That is number of moles of solute is mass of the solute by molar mass of the solute. Okay. So, if I am substituting this NB value here, okay, how I can write? Pi. Yes, pi will be equal to, instead of NB, I write WB by MB, right? Now, what is there? B is in the denominator, that I will write in the denominator itself. Now, what else is there? RT, that comes in the numerator, right? So, this is the equation that you can get WB RT by MB into V, where W is the mass of the solute, MB is the molar mass of the solute, right? And V is the volume of the solution, right? Now, if, as I said, if you have to calculate the molar mass, you can just rearrange the equation. This MB comes here and this pi comes down. You can just rearrange it and you can use this equation. MB is equal to WB RT by pi V. From this equation, you can calculate the molar mass of the solute, right? So, I hope it is clear. So now we are going to study about the different types of solution based on osmotic pressure, right? So the first one is isotonic solutions. So isotonic solutions are two solutions which are having same osmotic pressure, right? If they are having same osmotic pressure means osmosis will not be taking place, right? So if I am taking two solutions, neither the solvent will move from here to here or here to here. That means there is no osmosis taking place. So these are two solutions having same osmotic pressure, right? So two solutions having the same osmotic pressure at a given temperature are called as isotonic solutions. Now an example for it is, yes, it is red blood cells, that is our RBCs, is isotonic, that is the fluid which is present inside our cells. It is isotonic with 0.9% of sodium chloride. Okay, that is called as saline solution, right? The concentration of the fluid which is present inside the cell and 0.9% sodium chloride is having same osmotic pressure. So both of them are called as isotonic solutions, right? So which is called as normal saline. This 0.9% sodium chloride is called as saline, right? And it is used in injections instead of distilled water. Okay, so intravenously we do not inject distilled water. What is that we are injecting? It is 0.9% sodium chloride solution, because if we are injecting something which is having same osmotic pressure of that of the fluid which is present inside the cell, then no problem, right? No osmosis will take place, or else what would happen to the cell? Either it will shrink or else it will bulge, right? So if you are intravenously injecting something, that should be having the same osmotic pressure as of that of the fluid which is present inside the cells, right? So that is 0.9% sodium chloride. So this is about isotonic solutions. Now next is hypertonic solutions. Hyper, so that means it is having more osmotic pressure, right? So the solutions whose osmotic pressure is higher than that of the given solution is called as hypertonic solutions. Okay, so more than the given solution, right, the other solution will be having higher osmotic pressure. So that is called as hypertonic solution. Let's take an example for this as well, right? Same thing. So when the red blood cells is kept in seawater, or we can say more than a solution which is containing more percentage than 0.9% sodium chloride, what happens? Water passes out of the cell due to osmosis and the cell shrinks. So in the case of hypertonic solutions, yes, as you can see here, what happens, right? In the cells, that is the fluids present inside the cell is having a particular osmotic pressure, and we are intravenously injecting something which is having more concentration than 0.9% sodium chloride. That is a hypertonic solution we are injecting it. Okay, so now outside the cell, the concentration is more than 0.9%. Outside, it is not having same osmotic pressure, right? So outside the cell, more concentration is present. So what did we study about osmosis? It is the passage of solvent particles from lower concentration to higher concentration through a semi-permeable membrane. So where is having the lower concentration? It is inside the cells, right? Outside it is having more concentration than 0.9% NaCl. So what happens? Solvent particles will start moving out of the cell, right? From lower to higher concentration it will move. So the water, that is the solvent, that is the water, will start going out of the cell. So what happens? Your cell will shrink. Okay, so that is a problem, right? The cell should not shrink, right? So that is why this 0.9% sodium chloride is that much important, right? So if it is a hypertonic solution, that is more than 0.9% sodium chloride is injected, what happens? Yes, the solvent or the water will move out of your cell and your cell will shrink. Yes, so that is also a problem, right? Now let's discuss hypotonic solutions. Hypotonic solutions are solutions which are having less osmotic pressure than the given solution, right? It is having lower than that of the given solution. Osmotic pressure will be lower than that of the given solution. So same way, when the red blood cells is placed in a hypotonic solution, what happens? That is, if the red blood cell is kept in a solution which is having osmotic pressure less than 0.9% sodium chloride, that is the concentration is less than 0.9% sodium chloride, what happens? Yes, the water will flow into the cell because of osmosis, and to an extent what happens? It bursts also. Yes, that is also a dangerous situation, right? So let's take this diagram and understand it. In the case of hypotonic solution, hypotonic means, yes, less than 0.9% sodium chloride we are injecting. So what happens outside the cell? What is the concentration present? It is less than 0.9% sodium chloride, right? So where the concentration is more? Yes, now inside the cell the concentration is more and outside the cell the concentration is less. So what is osmosis? Flow of solvent particles from lower concentration to higher concentration. So what happens? The solvent, that is the water, will start flowing from outside to your cell. Yes, from outside, that is lower concentration, to inside the cell. So what happens? The cell will start bulging and at one instance it will burst also. Yes, so that is also a trouble. So I hope you understood what is isotonic, hypertonic and hypotonic solutions, and I hope you also understood the importance of this 0.9% sodium chloride. So this exact concentration should be intravenously injected. It can't be more than this. If it is more than this, what happens? The cell shrinks, and if it is less than that concentration, the cell will bulge and burst. Okay, yes, so I hope it is clear. Now moving on to the next topic, that is reverse osmosis. So till now we studied osmosis, osmotic pressure, and now we are going to study about reverse osmosis. So have you heard this reverse osmosis anywhere, right? The RO drinking water. So what is the full form of this RO? It is reverse osmosis, right? So that is a familiar thing for you, RO drinking water. So the full form is reverse osmosis, right? Okay, coming back, the process of reversing the direction of osmosis by applying the pressure higher than that of the osmotic pressure to the solution of higher concentration is called reverse osmosis. Yes, so we know osmosis and we know osmotic pressure. Osmotic pressure is applied on the solution side to just stop the flow of solvent. Okay, how much pressure is required to just stop the flow of solvent from the solvent to the solution side, right? Now, if we are applying more pressure, that is more than the osmotic pressure, right? Yes, if we are applying a pressure here, there is a piston through which you can apply pressure, right? So, if we are applying a pressure which is higher than the osmotic pressure, what happens? Now, it will reverse the osmosis process, right? So, actually it is supposed to move from lower concentration to higher concentration. Now, what happens? From the solution side, only the solvent will move from the solution to the solvent. So, now what is happening here? Only you will be able to get the water here, right? So, this is used in desalination of seawater. That means, yes, in seawater, what is there? Salt is there as well as water is here. This is the solution. So, if we are applying a pressure in the salt water, which is more than the osmotic pressure, right? Osmotic pressure, what it happens? It just stops the flow of the fresh water to seawater, right? Yes. So, if we are applying a pressure which is more than the osmotic pressure, what happens? The opposite take place. Yes, that is from higher concentration, it will start moving to the lower concentration through a semi-permeable membrane. So, we know that only the solvent particles will move through semi-permeable membrane, right? So, what happens? Solvent will move from salt water to fresh water. Right, so the salt will remain there, only you will be able to get the water, right? So in that way you will be able to get fresh water from the salt water. This is called as desalination of seawater. So that is an application of reverse osmosis. So I hope it is clear. So yes, what is happening? The direction of osmosis is reversed. That is from lower concentration, it is supposed to go to higher concentration. But when we are applying a pressure which is greater than osmotic pressure, the solvent particles will go in the opposite direction. That is from higher to lower concentration, right? Yes, okay. Now during reverse osmosis, the pure solvent flows out of the solution through the semi-permeable membrane, right? From here only the pure solvent is going, that is only the water is going here. The salt will still remain there, right? Yeah. Now reverse osmosis is used in desalination of seawater, right? And when pressure more than osmotic pressure is applied to the seawater, pure water is squeezed out of the seawater through the semi-permeable membrane. That is what we just discussed now. And a variety of membranes can be used. The semi-permeable membrane, a variety of semi-permeable membranes can be used for reverse osmosis. Cellulose triacetate can be used, right? And thin film composite membranes can also be used as semi-permeable membrane. Okay, so what you have to remember, semi-permeable membrane only allows the passage of solvent particles, right? So I hope you are clear with osmosis, osmotic pressure and reverse osmosis and its application, right? Now moving on to the last concept of this chapter, that is abnormal molar mass. Okay, so from the name itself, abnormal. What is abnormal molar mass? So actually through the experiment, what molar mass you are supposed to get, you won't be getting that exact value. Yes, it will be either higher than it or lower than the molar mass which is expected, right? So the molecular masses of the solutes can be calculated by measuring any of the colligative properties of dilute solution, and these methods are applicable only if, right, the solution is dilute so that the Rolle's law is obeyed, right? Yes, so we are talking about molar masses of the solute. So as I said, the molar mass that we are calculating, how do we calculate it? It is through the various colligative properties that we discussed, right? The 4 colligative properties. So the molar mass that you are calculating, it will not be equal to the expected molar mass, right? So if you have to calculate it through the colligative properties, first one is the solution should be dilute so that you can apply the Rolle's law, and the next one, the solute is non-dissociable or non-associable in the nature. That is, it should not undergo dissociation or association. If it is not undergoing dissociation or association, yes, the molar mass, there won't be any change, right? Now, in case of solute which either undergo dissociation or association, molecular masses of the solutes is determined by these methods will be abnormal. Right? So actually you are supposed to get the perfect value through the colligative properties calculation. But when dissociation or association is taking place, you will get abnormal molecular mass. That means either it will be more or less than the expected value. So that is abnormal molar mass, right? So let's take the first case when association of solute molecules is taking place. Okay, so certain solutes in solution are found to associate, right? And this leads to the decrease in number of molecules of particles in the solution. So if the number of particles is decreasing, what happens to the colligative property? Yes, the colligative property also decreases, right? Yes, thus it results in a decrease in colligative properties. So number of mass of solute particles is inversely proportional to the colligative properties. So if colligative property is decreasing, that means yes, the mass of solute increases. Clear? Right? So what is happening here? Yes, 2 particles, if I am saying 2 molecules are there, they are associating and it becomes 1. Okay, 2 molecules is acting as 1 molecule means, yes, now instead of 2 there is only 1 molecule. So what happens? The number of particles is less there. Number of particles is less means colligative property is less. Colligative property is less means molecular mass will be more. Okay, so rather than the expected value, in this case when the solute particles are undergoing association, the molar mass will be more than the expected value because the colligative properties are less, right? So therefore, molecular masses determined will be higher than the normal values for molecules or for the solutes which undergoes association in solution. So let's take this example. Acetic acid in benzene undergoes dimerization. So as you can see here, there are 2 molecules of acetic acid, right? 2 molecules, as you can see in this diagram, CH3COOH. This is one molecule and this is the another molecule. 2 molecules of acetic acid. Now what happens? It dimerizes. 2 molecules are combining means it dimerizes. If it was 3, it was trimerizing. Okay, so dimerization process take place and now it acts as just 1 molecule. Instead of 2, now it is 1. So what happened? Dimerization took place. It became or it acts as 1 molecule. So the number of particles is less. So colligative property also becomes less. So colligative property is becoming less means molar mass is increasing. So when the solute particles are undergoing association, okay, when they are undergoing association, the molar mass will be greater than what it is expected, right? So now moving on to the next one, that is dissociation. So certain molecules in solution are found to dissociate, right? So this leads to the increase in number of particles in the solution. So that means they dissociate. From 1, they are becoming 2. Okay, so that means let's take this example. There is 1 mole of sodium chloride. So we know that sodium chloride in the solution, it dissociates into Na plus and Cl minus. So from 1, you are getting 2 particles, right? Now the number of particles has increased. Here it was only 1 sodium chloride. Now it became Na plus and Cl minus. So what is happening? The number of particles is increasing, right? During dissociation, what happens? Number of particles increases. So if number of particles increases, what happens to colligative property? Right? Colligative property depends upon the number of moles of solute, right? So if the number is increasing, what happens to the colligative property? Colligative property increases. That means what happens to the molar mass? Molar mass decreases. So if the solute particles in a solution are undergoing dissociation, what happens? The molar mass decreases because the colligative property is increasing there. So therefore, molecular mass determined will be lower than the normal values for molecules undergoing dissociation. So I hope it is clear. So if the solute particles are undergoing association in the solution, what happens to the molar mass? What happens to the molar mass? It is more than what it is expected, right? And if it is undergoing dissociation, okay, if the solute particles are undergoing dissociation, the number is increasing. So what happens? Colligative property also increases, but the molar mass decreases. So what does that mean? Than the expected value, the molar mass will be less. So I hope it is clear. The relation between association and molar mass and dissociation and molar mass. Now to calculate this, Vanthof factor was introduced. Right? So how much dissociation or to what extent the dissociation takes place or what extent the association takes place, to measure it, calculate it, yes, a Vanthof factor was introduced. So in 1886, Vanthof introduced a factor which is called as Vanthof factor, which is represented by the letter small I. Okay. Yes, to express the extent of dissociation or association of solutes in a solution. So to what extent this dissociation or association will be taking place. Okay. So how you can calculate it? Vanthof factor I will be equal to the normal molecular mass divided by observed molecular mass. Okay. So what it was supposed to be, that is the normal molecular mass, right? The expected one. And what did you observe? Yes, observe the molecular mass. That ratio will give you Vanthof factor, right? And then another way is observe the colligative property by calculated colligative property. Yes, we know through colligative property calculations, we can calculate the molar mass, right? So, yes, what is the observed one divided by, yes, what you calculated and what you found it, the ratio between them will give you Vanthof factor. Either of this will give the Vanthof factor, right? I hope it is clear. So now what you have to remember is the I value, that is the Vanthof factor, will be greater than 1 for the molecules or for the solute particles which undergo dissociation, and I value will be less than 1 for the solute particles which undergo dissociation. Okay, and if it is undergoing neither association or dissociation, so what happens if the solute particles are neither undergoing association or dissociation? It will be equal to 1. Right. So what you have to remember, Vanthof factor, how you can calculate with either of this equation, and if the I value that is calculated is greater than 1, that means the solute particles are undergoing dissociation, right? And if it is less than 1, it is association, and if it is equal to 1, it neither undergoes association or dissociation. So that means the molar mass will be the correct itself. That is, it doesn't have an abnormal molar mass. When this abnormal molar mass is happening, because either it is undergoing association or dissociation, right? So I hope it is clear. Now this Vanthof factor is being introduced into the 4 colligative properties, right? The introduction of the Vanthof factor modifies this 4 colligative properties. We know that abnormal mass also has to be included in the calculation of the molar mass, right? So what do? We introduce this I factor into each of these equations, right? So relative lowering of vapor pressure, what was the equation? P1 naught minus P1 by P1 naught is equal to chi B. So here the I is introduced for the same equation. So elevation of boiling point, delta TB is equal to KB into M, right? So I is again introduced here. So it becomes delta TB is equal to I KB M. Right, depression in freezing point becomes delta TF is equal to I into KF into M, right? So for osmotic pressure, we know the equation is pi is equal to C RT, right? So C you can write it as N2 by V. What is left here? RT. So it can be written as pi is equal to I. Yes, the Vanthof factor is also introduced. Pi is equal to I into N2 RT by V. Yes, so the Vanthof factor is also being introduced in this different colligative properties to calculate the molar mass. So I hope it is clear. So I hope what and all we have discussed in this session is clear for you. So in the next session, we will be discussing the numericals separately on all the 4 colligative properties. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.